Hello friends, in module number 1 we have seen the chain surveying, in module number 2 we have seen the compass surveying, and in module number 3 we have seen the plane table surveying. So all these surveying, they are related to the measurement in the horizontal plane, and we are not going to have the measurement in the vertical plane. Then we have seen the module number 4, and it is related to the leveling and its application. And whenever we are saying that it is leveling and application, means we are going to consider, or we are going to take the measurement in the vertical plane, not in the horizontal plane. So basically this is the major difference between surveying and leveling. So in the surveying we are trying to get the measurement in the horizontal plane in the form of linear measurement as well as angular measurement, whereas in case of leveling we are trying to get the angle in the vertical plane. We are going to take the linear measurement in the vertical plane. So this is module number 5, and in this module number 5 we are going to consider the theodolite surveying, and again it is a part of surveying in which we are going to consider the measurement in the horizontal plane, and some experiment we are going to consider in the vertical plane. This slide refers to sectional view of a theodolite, and the theodolite has been divided into 3 component part of the theodolite. It is leveling head assembly, then horizontal circle assembly, and allied assembly. So in this slide you will observe the vertical axis. The vertical axis is the axis which is passing through the center of the instrument, and then we are having the objective and the telescope, then the altitude bubble. So whenever we are interested to record the horizontal angle as well as vertical angle, then the plate bubble as well as altitude bubble should be at center. Otherwise there are some errors which are to be introduced. Then we are using the vertical clamping screw in the Tronin axis, or we are going to call it as a horizontal axis of the telescope, and it is the axis which is going to make a 90-degree angle to the line of sight. Again there is a vertical circle wherein we are going to measure the angle ranging from 0 to 90 degree. It carries the vernier C and vernier D, and whenever the line of sight is horizontal, you will observe 0 degree on vernier C and 0 degree on vernier D. And whenever we are setting the vernier C and D to 0 degree and 0 degree, we are going to tighten the vertical clamping screw so that our line of sight will be horizontal. Then we have got a plate level, and whenever we are making the line of sight horizontal, then in order to maintain the vertical axis should be perpendicular to the line of collimation, we are supposed to bring the plate level plate bubble in the level tube at the center. And once it is at center, then we can see that the vertical axis and the line of collimation is going to make an angle of 90 degree, and then only we are going to record the angles for horizontal angle as well as vertical angle. Here we are going to see why the theodolite surveying is more precise than the compass surveying. So far we have been measuring the horizontal angles by using a compass with respect to meridian, which is less accurate, and also it is not possible to measure vertical angle with a compass. So when the objects are at a considerable distance or situated at a considerable elevation or depression, it becomes necessary to measure horizontal and vertical angles more precisely. So these measurements are taken by an instrument known as theodolite. So theodolite is more precise than magnetic compass, as the magnetic compass measures the angle up to an accuracy of 30 minutes. However, vernier theodolite measures the angle up to the accuracy of 10 seconds or 20 seconds depending upon the graduations marked on the horizontal circle assembly as well as vertical circle assembly. This slide refers to theodolite surveying. The system of surveying in which the angles are measured with the help of a theodolite is called theodolite surveying. So in this slide we are going to see the theodolite as the most accurate surveying instrument used for different purposes, such as measuring horizontal and vertical angles, locating the points on the line, then prolonging survey lines, further finding difference of level, then setting out grades, then ranging curves, and in tachometric surveying. Again, in this slide you are going to observe the different part of the theodolite, and this is a transit vernier theodolite, and in which the vertical axis, tuning axis is shown. And whenever we are going to use this particular instrument, then there should be a perfect relationship between the fundamental lines of theodolite. Here in this slide we are going to observe the fundamental lines such as vertical axis, line of collimation, horizontal axis, and the various assemblies involved in the theodolite. They are elided assembly, horizontal circle assembly, and leveling head assembly. They are shown in this particular sketch. A transit theodolite is one in which telescope can be rotated in a vertical plane. So in this slide you are going to see the upper plate and lower plate assembly, and which is used for measurement of horizontal angle, wherein the vernier A and vernier B, they are provided, and whenever we are going to use this particular lower plate as well as upper plate assembly for measurement of angles, first of all we are supposed to set the vernier A to 0 degree and B to 180 degrees, so that it is possible to start the measurement of horizontal angle. And whenever we are interested to record the angle change, then we have to loose the upper clamp screw, and then we have to rotate the telescope in a desired direction, so that we are going to record the angle which is reflected in the upper plate reading as well as lower plate reading. This slide refers to the different fundamental axes of the theodolite. One is vertical axis, another is horizontal axis, and the line of sight. And whenever you are trying to observe the relationship between these fundamental lines, you will observe that the vertical axis is going to make an angle of 90 degree to the horizontal axis. At the same time, it is going to make an angle of 90 degree to the line of sight or sight axis. And here in this particular figure, you will observe that the line of sight is going to make an angle of 90 degree with the horizontal axis. This is more important. So in this slide we are going to see the classification of theodolite. The theodolites may be classified as transit theodolite, non-transit theodolite, then vernier theodolite, and micrometer theodolite. These are the four categories of theodolites. So in this slide we are going to see the classification of theodolite. First is transit theodolite. A theodolite is called a transit theodolite when its telescope can be transited, that is revolved through a complete revolution about its horizontal axis in the vertical plane, whereas a non-transit type theodolite is the type of theodolite in which the telescope cannot be transited. They are inferior in utility and have now become obsolete. Then the next type of theodolites are vernier theodolite. For reading the graduated circle, if verniers are used, the theodolite is called as vernier theodolite, whereas if a micrometer is provided to read the graduated circle, the same is called as micrometer theodolite. Vernier type theodolites are commonly used. This slide shows the types of theodolite may be categorized into non-transit theodolite, transit theodolite, then vernier theodolite, and micrometer theodolite. This slide refers to non-transit theodolite, wherein it is not possible to rotate the theodolite about its horizontal axis. Whenever the students are instructed to prepare a sketch of theodolite, then they may refer this particular diagram. In this slide we are having the digital theodolite, the image which is shown, and in the particular slide the Nikon's digital theodolite has been shown. Then the next type of theodolites are vernier theodolite. For reading the graduated circle, if verniers are used, the theodolite is called as vernier theodolite, whereas if a micrometer is provided to read the graduated circle, the same is called as micrometer theodolite. Vernier type theodolites are commonly used. So in this slide we are going to see the important features of total station. First is keyboard. Keyboard control all the functions operated by keyboard. Then digital display displays the values of distance, angle, height and coordinates of the observed point where the reflector is kept. Then remote height object. The height of some inaccessible objects such as towers can be read directly. The microprocessor provided in the instrument applies the correction for Earth's curvature and mean refraction automatically. Then traversing program. The coordinate of the reflector and the angle or bearing on the reflector can be stored and can be recalled for next setup of instrument. Then setting out for distance, direction and height. Whenever a particular direction and horizontal distance is to be entered for the purpose of locating the point on the ground using a target, then the instrument displays the angle through which the theodolite has to be turned and the distance by which the reflector should move. Then some of the modern surveying instruments, they are ADMs. The distance measurement of distance and their direction can be obtained by using electronic instruments that rely on propagation, reflection and reception of either light waves or radio waves. They are infrared wave instrument, light wave instrument and microwave instrument. Here in this slide we are going to see the total session. It is a lightweight, compact and fully integrated electronic instrument combining the capability of an EDM and an angular measuring instrument such as wild theodolite. It can perform the following functions, that is distance measurement, angular measurement, data processing, digital display of point details, and it is going to store the data in an electronic field. Then the size of theodolite. A theodolite is designated by diameter of graduated circle on the lower plate. The common sizes are 8 cm to 12 cm, while 14 cm to 25 cm instruments are used for triangulation work. Greater accuracy is achieved with larger theodolites as they have bigger graduated circle with large divisions, hence used where the survey work requires high degree of accuracy. So this slide refers to description of transit theodolite and the essential part of the transit theodolite. They are leveling head, lower circular plate, upper plate, telescope, vernier scale, T-frame, plumb bow, tripod stand. In this slide we are going to see the parts of theodolite. First is leveling head. So leveling head is used to attach the instrument to tripod and attach the plumb bow along the vertical axis of the instrument. Then second part is lower plate oblique circle plate, an annular horizontal plate with graduations provided all around from 0 to 360 degree in a clockwise direction. The graduations are in degrees divided into 3 parts so that each division equal to 20 minutes. Horizontal angles are measured with this plate. The size of theodolite is defined by the diameter of horizontal circle. Then the upper plate. Horizontal plate of smaller diameter provided with 2 verniers on diametrically opposite part of its circumference. These verniers are designated as A and B. They are used to read fractions of the horizontal circle plate graduations. The verniers are graduated in 20 minutes and each minute is divided into 3 to 5 parts, making least count of 20 seconds or 10 seconds. This slide refers to non-transit theodolite, wherein it is not possible to rotate the theodolite about its horizontal axis. Then the plate level. Spirit level with the bubble and graduation on glass cover. Single level or two level fixed in perpendicular direction may be provided. The spirit can be adjusted with the put screws of the leveling head. Then next part is telescope. The essential part of the telescope are eyepiece, diaphragm with crosshairs, object lens and arrangement to focus the telescope. Then the vertical circle. The circular plate is supported on horizontal axis of the instrument between the A-frames. Vertical circle has graduation ranging from 0 to 90 degree in 4 quadrants. Vertical circle moves the telescope when it is rotated in the vertical plane. Then vertical circle clamp and tangent screw. Clamping the vertical circle restricts the movement of telescope in vertical plane, whereas tangent screw allows some movement in the vernier C and vernier D. Then altitude level. A highly sensitive bubble is used for leveling, particularly when taking the vertical angle observation. So whenever we are going to record the vertical angle, then the bubble in the altitude bubble should be at the center. At the same time, the plate bubble should be at center position, and then only it is possible to record the vertical angle, and whatever the angle we are going to record, with the help of that is free from any errors. So again in this slide I have tried to show the different fundamental axes. One is vertical axis, another is horizontal axis, third is axis of telescope, and the graduation on the vernier C and vernier D, how the vertical angle is recorded. At the same time, horizontal circle graduations. The graduations are generally in a clockwise direction. They are graduated, and we are going to record the angle with respect to a particular direction by setting the vernier C to A to 0 degree and B to 180 degree. So in this slide we are going to see how to take a reading for the measurement of horizontal angle. And generally for measurement of horizontal angle we are going to refer the horizontal circle assembly, wherein you will find that the graduations are marked starting from 0 and it is going to end at 360 degree in a clockwise direction. So in the main scale, so this is the main scale, and on the main scale generally the readings obtained for the horizontal angle may be in degrees and minutes, whereas when we refer the vernier scale, we can get the readings on the vernier in minutes as well as seconds. So the total angle we have to record is to be taken from the main angle, that is degrees from the main scale, whereas we have to add, or we have to make a summation of angle in minutes from main scale plus the angle observed in the minutes on vernier scale, and whatever the seconds we are going to get on the vernier has to be considered, so that whatever the total horizontal angle we can receive may be in degrees, minutes and seconds. Then the next type of theodolites are vernier theodolite. For reading the graduated circle, if verniers are used, the theodolite is called as vernier theodolite, whereas if a micrometer is provided to read the graduated circle, the same is called as micrometer theodolite. Vernier type theodolites are commonly used. So here this slide refers to the graduation of vertical circle, and the graduations are made in an anti-clockwise direction as well as clockwise direction. So thank you friends.